I'm going to keep one of these. Thanks, Adam. So I'll just start by recalling a bit of spin helicity in case people have, since there was a gap one day. So toward the end of the last lecture, we saw that we started working in complexified Minkowski space, C13, and we saw that on C13 we can define solutions of the Laplace equations as complex momentum eigenstates that look like plane waves e to the I p dot x, whose null momenta can be decomposed into spin helicity variables. So p alpha alpha dot. I'm not writing the explicit matrix expression for p alpha alpha dot, but basically the end result was that you can decompose it in terms of a pair of independent complex two spinors. And in the last lecture, I also gave some explicit expression, but at the end of the day, this choice of two spinors is defined only up to little group scalings that look like this. 1 over S, 1 with 2 for S and C star. C star are just complex numbers without the origin. Now, I'll come to so as you've probably seen in Guy's talk and other talks, these spin helicity variables are very useful for writing down expressions for amplitudes. I'll come to that in my fourth lecture. Right, in this lecture and the next, I want to build up some formalism of the formalism of twistor theory and basic translations of your differential equations of everyday life, like the Maxwell equations and the Einstein equations in terms of these spin helicity variables. So one of my hopes is that you could probably, even if you don't end up caring about twistor theory at the end of the day, you might still be able to understand papers when you come across anything that works with spinor notation. Okay, so so in this lecture mainly I'll just tell you what twistor space is. So to define a twistor, we first ask ourselves, here we have defined the spinor helicity variables for momenta. Now, momentum is a conserved quantity. If you're dealing with a massless particle traveling in flat space, what are the various conserved quantities that that particle has? What are the conserved quantities of a particle traveling freely in flat space, other than momentum? This is for momentum, so other than momentum. Yeah, so basically I'm going to say angular momentum, so spin. So just like you defined spinor helicity variables for null momenta here, it's natural to ask, I guess Roger Penrose asked this in his paper, but probably he wasn't the first person to do it. Can we define spinor helicity variables for angular momentum? This is a natural question because you want to formulate everything that you're doing, especially the notion of spin and spinning particles in terms of spinors. So, what is angular momentum? In your usual everyday four component notation, it's just XA PB minus XB PA. So, at the moment, I'm just thinking of a classical particle, and X is the instantaneous position. So, that's the expression for the angular momentum in your usual four momentum vector, the tensor components. But now you can define its spinor components in a completely analogous way. You have defined the spinor components of X and P, so you just plug those in. So that defines a spinorial version of angular momentum. Now you ask if you can find a nice decomposition of this object into smaller two spinors. At the moment, this is basically written in terms of these two component matrices, but can you decompose this in terms of, can you repackage this in terms of smaller two-spinners? So I'll probably do a little bit of this in the discussion session.
When you say two-spinners, so as in, are you going to try and reformulate it in terms of the language of angular square brackets?
Yeah, basically, when I say two-spinners, I just mean objects with a single spinner index. Two meaning two component spinners rather than, so that's just, yeah, balance.
Question? But would you put two component spinners for x? Because x squared is not usually x squared.
Yeah, so the decomposition will be slightly different. Yeah, you'll get those x alpha alpha dot lambda alpha as being one spinner. Anyway, we'll get to that. So, firstly, even before I start plugging in things, okay, I'll just plug in that expression in minus the other way around. Even before I start plugging in things, let's just try to use the antisymmetry of m alpha alpha dot beta beta dot to sort of reduce this into its irreducible SU2 representations. So m alpha alpha dot beta beta dot satisfies the antisymmetry that if you think of beta beta dot and alpha alpha dot as composite indices and exchange them, you get a minus. This just follows from its definition, that definition. And now, you can basically use that to show the following. If you have any, so you don't need to use the explicit expression for the angular momentum there. Suppose you just had that antisymmetry property, you can show that any tensor with that property can be decomposed into irreducible representations of SU2, SL2C, sorry, which and the decomposition looks something like this. So I introduced Levi-Civita symbols in the previous lecture. So epsilon alpha beta is just 0, 1, minus 1, 0, the same. The matrix epsilon alpha dot beta dot as a matrix, it's the same thing. And in terms of these, you can decompose it like this. Epsilon alpha dot beta dot m alpha beta, where the irreducible objects m and m tilde are symmetric in their spinor indices. So m alpha beta equals m beta alpha, and m tilde has the same property. You can easily check that if you exchange this composite index with this composite index, then you get a minus sign from the exchange of the alpha beta through the Levi-Civita. So you need this to be symmetric because you don't want to generate an extra minus sign. So let me just sort of give you one or two steps in how to derive this, but I'll give it as an exercise. So basically, what you do is you can read off. So basically, you have to derive these expressions for m alpha beta. M alpha beta is epsilon alpha dot beta dot m alpha alpha dot beta beta dot over 2. How do you see that? You basically take epsilon alpha dot beta dot. If you contract this into this epsilon alpha dot beta dot, you can show by taking the trace of the matrix that this is exactly equal to 2. And what happens here is that you use this fact, you use the symmetry of m tilde to set that term to 0. So basically, if you contract with epsilon alpha dot beta dot, the first term drops out and only the second term survives. And up to a factor of 2, you get this definition of m alpha beta. And similarly, you get the definition of m tilde alpha dot beta dot by contracting through with epsilon alpha beta. So basically soaking up the indices that you don't want. And yeah, I'll show you in the discussion exactly why these are the only things that sort of enter in this decomposition. But yeah, any question about this manipulation. So there are some basic spinor trickeries that you learn, that you sort of absorb over the course of time. This is one of them. Use symmetry, antisymmetry. I suppose you've seen this kind of things in GR, but it's a nice reminder. Any questions? That was just... So, once I have those formulae, I can now start plugging. So, okay, the point was that this formula is valid just by the virtue of the antisymmetry of m in alpha alpha dot beta beta dot. But now I can plug in the explicit expression for the angular momentum in spinor coordinates and see what I get. Just to give you some names, m alpha beta will correspond to the negative helicity part of the angular momentum, and m tilde alpha dot beta dot will correspond to the positive helicity part of the angular momentum. So basically what happens at the end of the day is that a positive helicity particle is defined as something which has a non-zero J3 eigenvalue of this object, but is annihilated by this object, and the other way around. Okay, so what are the explicit expressions for this decomposition? M alpha beta, as I said, is, which one do I want to do? Let's do M tilde. We like positive helicity. Epsilon alpha beta m alpha alpha dot beta beta dot, which is half epsilon alpha beta x alpha alpha dot lambda beta lambda twiddle beta dot minus the other way. And now you remember the spinor contraction rules, the spinor raising and lowering rules. So in the last lecture I gave you some rules that look like epsilon alpha beta, well, lambda beta, epsilon alpha beta will actually be minus of lambda alpha in my conventions, and similarly for the other part, lambda beta, lambda alpha, epsilon alpha beta will be lambda beta. So you use these index raising rules to simplify this. So you get half x alpha alpha dot, let me know if my font is too small, half x alpha alpha dot, lambda beta contracted into epsilon alpha beta, so that gives you a minus sign, lambda alpha, let me put a bracket here because this is the important quantity, times lambda tilde beta dot minus half x beta beta dot lambda beta lambda tilde alpha dot. Now beta is a dummy index, so you can replace it with alpha. It's fun to do these at least once in life, then you can quickly forget about them. If I start boring you, I can skip them. So this just gives you, now alpha was a dummy index. You notice that both terms are really the same term, but you just have a symmetrization over alpha dot and beta dot. So you just get minus, let me take this lambda tilde alpha dot here, alpha dot beta dot alpha lambda alpha. The half goes into defining the symmetrization. So that's my expression for m tilde alpha dot beta dot. As promised, that's symmetric in alpha dot and beta dot.
How do we exchange the alpha and beta dot indices on X? Can you just change the...
I didn't, sorry, maybe the dot is invisible.
No, but in the first line, on X, the alpha dot index is the second index.
Yes.
And then in your final equation, the alpha dot index is the first index.
Oh, sorry, I'm an idiot. I tried to write it neatly, but I didn't. Sorry. Yeah, write it the other way around. Thanks. you have x alpha, alpha dot, lambda alpha, lambda twiddle beta dot. I was just trying to write it neatly, but you're exactly right. Thanks. Exchanging them would mean taking a transpose or something. Anyway, so any questions about this derivation? Again, the point is, I was just trying to give you an idea of these spinor calculations. I don't just want to tell you, I don't just want to leave everything at motivation. Okay.
So, just wondering if the spinors are treated as Grassmann.
No, everything is bosonic here. I'm not dealing with spinor fields. These are just like literal two-component vectors, yeah. Okay, so we find the expressions that m tilde is that, and similarly m alpha beta you find to be minus lambda alpha, well, okay, the natural other object, lambda tilde alpha dot. Now, we define a twistor. So, to define a twistor, first define a variable, a new variable that contains the spinor helicity data of angular momentum. So, you define this variable. Okay, yeah, you can now guess what I'm going to do. Lambda tilde and lambda we've already defined. What I'm going to do is just use this contracted object as my new two-component spinor. So you define mu alpha dot as a new spinor helicity variable. Call it x alpha alpha dot lambda alpha, and you define another one mu tilde alpha, and you call it. You define it by saying that this is equal to minus of, the minus is a convention, x alpha alpha dot lambda twiddle lambda tilde alpha dot. So these are my spinor helicity, you can say, variables for angular momentum in conjunction with lambda and lambda tilde. So you need all four objects. And in terms of these, you find the neat expression that m alpha beta, m tilde alpha dot beta dot is minus of mu alpha dot lambda tilde beta dot, all symmetrized, and similarly for the other object. So this is how, for example, Roger Penrose motivated twistors or defining these variables in his paper from the 1960s. And well, just the mu's and mu tildes by themselves don't have a name. But now what we're going to do is we're going to sort of package the data of momentum and angular momentum into two chiral halves. We are doing everything chirally, so that's quite natural. And that will bring us to the definition of a twistor. So basically, you package this data into a chiral and an antichiral half. Defined like this. So you define a twistor as this four-component object. So Z, A, where A is now going to be a composite four-component index. I will never use it explicitly, but I'll write it once. And a twistor is basically this combination. Basically, just take mu alpha dot and lambda alpha and make a four-component object out of them. And similarly, you define a dual twistor in the completely analogous way by taking the other half of the momentum, angular momentum, spinor data. And it's natural to put a dual index here because everything is sort of complex conjugated, though everything is, of course, complexified, so they're unrelated. So you have lambda twiddle. So yeah, so in some sense, these are the dual indices. Alpha dot is upstairs, alpha dot here is downstairs. And similarly, in the second half, you write mu tilde alpha, which is dual to lambda alpha. Okay, so this is how I define, or this is how twistors are defined in the literature. Of course, this is one way to motivate twistors. If you read through the literature or dare to go through 16 hours of Nima's lectures, then you will find that there are other, like representation theoretic ways to define twistors. For example, twistors are the variables in terms of which the conformal group of four-dimensional spacetime acts very naturally. And there's a lot of nice, I'll give another motivation in the next lecture, which has to do with solving linear field equations on spacetime by working directly on this twistor space. So another motivation comes from the fact that from Prahar, you've already heard that you want to try to build a theory in some dual auxiliary space like the celestial sphere, which you hope is this. So the celestial sphere is the space of on-shell data. The null momenta point towards the celestial sphere and label points on the celestial sphere. And you would hope that you could build a theory that directly works with this on-shell data and forgets about the off-shell dynamics in the bulk of space-time. The philosophy is somewhat similar here. Roger Penrose wanted to define some sort of auxiliary world. In this case, the space of these capital Z's, say, just take this chiral half, and he asked the question, can we find a way to represent the quantum mechanical physics of space-time, all the off-shell states, everything, in terms of just some simpler, maybe on-shell data, but maybe something else, some other dual encoding that might help us in solving problems that we find very hard to solve in terms of just space-time formulations. So again, this was discovered sort of constructed in the 1967. I think the paper is called Twistor Algebra by Penrose. So you can imagine that I'm not going to cover 50 or 60 years of physics in this lecture course. I'm going to very quickly jump to, I'll give you a slice of what was done in the 80s, and I'll jump to amplitudes. Okay, in any case, these, coming back to actual calculations, these satisfy the nice property that ZA WA equals 0. You can check that if you like. That's why I put that minus sign there. So basically you have mu alpha dot. This is defined just by component multiplication. Lambda alpha mu tilde alpha equals x alpha alpha dot lambda twiddle minus, so the minus now comes from my convention, lambda alpha x alpha alpha dot lambda tilde, and that's 0. So they're constrained. So the twistor dual twistor data of a single massless particle is constrained by this neat constraint, and this you can just call this z dot w if you like.
So, question. So when you say you forget about the off-shell data, so you have in mind that you have already taken care of say, divergences, etc. Like for example, to deal with
The divergence. Oh, you're meaning in the diagrams? Yeah, the hope with somebody like Nima, especially if he hears lectures, the hope is that you would find a way to not regulate the divergence. That will always be there. The calculation is the calculation, but to get at the Feynman diagrams themselves in a different way. So you will have to do the regularization. You can't get away with quantum field theory itself. But you want to get the answers that you get from space-time perturbation theory, Feynman diagrams, in some alternative, more efficient way. Maybe a diagram of some other quantum field theory on twistor space or something like that that might encode That might make your life easier. But you will have to deal with the divergence. That doesn't go away. So I suppose Roger's dream was to find some UV complete theory of gravity in terms of the geometry of Twistor space, but that hasn't exactly come to fruition. Anyway.
So are we to think of this twistor and dot twistor, the twistor as being a vector in twistor space and the dot twistor as being a covector?
Yeah. So in a dual twistor space. Yeah, exactly. So in fact, I'm not going to think of them as 4 vectors. They're actually going to be defined only up to overall scalings, which comes from little group scaling invariance, little group scaling covariance. So recall that I had lambda alpha. This was S lambda, S inverse lambda tilde. And now this acts using these definitions of mu and mu tilde. You now read off the little group scalings of mu and mu tilde. So mu alpha dot maps to, so if you take this map, then mu alpha dot scales the same way as lambda, and mu tilde scales the same way as lambda tilde. So now what I'm going to do is, I'm just going to take a chiral half of these variables and just work with their space. So I'm going to implement this scaling on just the chiral half. So I'm going to think of the z's, which is mu lambda, as defined up to. Okay, this is another nice property of the definition of Twistor. Lambda and lambda tilde are defined through the scaling that takes lambda up and takes lambda tilde down. But now on the Twistor, the scaling acts in a homogeneous way. So mu goes up and lambda goes up as well. So basically, you can think of this as rescaling the whole 4 vector. So ZA is now defined up to overall rescalings by non-zero complex numbers. And this brings down, so originally you can think of the ZAs as being defined in C4. But this scaling covariance, once you take that into account, you just start working with this quotient space of C4 by this C star. So it's not with one caveat that, so what you want to do is Twistor space is the space where such spinor helicity data lives, just the first part, the mu and lambdas. Is defined as the space of 4 vectors ZA, alpha dot lambda alpha, that satisfy lambda alpha not equal to 0. The point being that we want to work with non-trivial momenta. If you take lambda alpha equals 0, that's just 0 momenta. Even in the soft limit, we want to take it soft rather than like identically set it to 0. Modulo the quotient that I just introduced. So you quotient out by overall rescalings. Let me just grab some water. Explicitly, the space of mu alpha dots is C2. The space of lambda alphas is C2 minus the origin of that C2. That's the only subtlety here. Modulo this C star action that scales this overall in the same way. So that's what is Twistor space. Any questions about this definition?
By C star, do you mean all complex numbers plus 0?
All complex numbers except 0. Exactly. Let me write that down at least once. Thanks. Now, maybe I don't have enough time. Of course, I always overestimate myself. So I'm going to tell you a little bit about projective spaces. quickly.
So here you didn't talk about WA, the idea that that's a completely separate space in which the WA.
Yeah, so Roger's idea, okay, so there are many ideas philosophically. Roger's original idea was that you would try to construct a dual theory purely on the space of mu's and lambdas, because in some sense mu's are the same number of variables as the lambda tildes, and you want, even in celestial holography, you want to construct a theory on the space of lambda and lambda tilde in real Minkowski at least. So Roger's analogous argument was that you would only need to construct a theory on the space of the lambda and the mu. But life is hardly ever that simple. So there are these ambi-twistor constructions, where ambi-twistor space is the Cartesian product of twistor space and dual twistor space, both z and w's, modulo this z dot w equals 0 constraint. So sometimes you have to do ambi-twistor strings, which I'll do in my last lecture. And they seem to be the real nice thing. And none of us really know why this extended set of degrees of, this double set of degrees of freedom is actually being needed. But somehow they're the most efficient thing to do. We'll come to that maybe in the last lecture. But like people like us, we would like to define something purely on the space of kinematic data, lambda and lambda tilde. We don't want to. Again, 60 years of physics and math. So projective spaces, let me talk about them a bit. Basically, I'm going to embed my twistor space into what is called complex projective 3 space. So complex projective n space is defined in a very similar way. This is just this set of n vectors. Z naught, I'm just using little z's here, not to confuse with the twistor, up to Zn in Cn minus the origin modulo the rescalings. Z naught up to Zn equivalent to S times Z naught up to Zn, where S is in C star. So you have to subtract 0 from here because C star acts stabilizes 0, so the quotient is ill-defined. If you don't understand that, don't worry about it. I subtracted 0 from half of this space, so that's automatically done here, so you don't need to worry about that. But other than that, elements of, so this is complex projective n space, elements of this has complex dimension n. Basically, oh sorry, this should be n plus 1. So what have I done? I've taken an n plus 1 vector and quotiented out by a scaling, so that reduces the dimensionality to n. And now we are going to deal with the two simple examples. Elements of CPN are usually denoted like this. Sometimes you'll see this notation, or sometimes you'll see ratio notation, because you think of this as this n vector, but all of them are taken up to an overall scaling, so it's a ratio in some sense. I'm not going to use either. I'm going to deal with two specific examples. I can use subboard, CP1 and CP3. CP1 is just the case where you start with C2 and have CP1 is secretly the two-sphere. What happens is you start with some vector z naught z1 in C2 minus the origin, and you quotient out by C star. So what you can do is you can coordinatize it by either a stereographic coordinate z equals z1 over z naught. In the patch where z naught not equal to 0, this is well defined. Or you can coordinatize it by 1 over z equals Z1 equals Z0 over Z1, which is well defined in the patch where Z1 is not equal to 0. And this happens to be the same stereographic notion of coordinates on a two-sphere that you might be familiar with. You have a sphere, you can excise the north and south poles, you have one patch that covers the north pole and another patch that covers the south pole, and you have stereographic coordinates Z on it, on one patch and 1 over Z on the other patch. People may have come across this in other contexts. So CP3, so I should have used lambda 1, lambda 2 because I'm going to use that notation here. So you think of lambda alpha as living in CP1 because that's your complexification of the celestial sphere. CP3 is where our twistor space is going to be naturally embedded. Also, if you're not following this geometry, don't worry too much about it. You can think about the z's as just 4-component objects because at the end of the day, we'll do calculations with the 4-component vectors, z's, rather than any other coordinate system on this space. That's the real power of using homogeneous. These are called homogeneous coordinates on projective spaces. So these n+1 coordinates on an n-dimensional space, they're really good because you can sort of cover all the patches and they can act as global coordinates in your projective space. So CP3 is the space of capital Z's in C4. Now notice I'm using the same capital Z for a reason, up to the same C star scaling. Z is equivalent to SZ. And the idea is that that space, PT, embeds into CP3 in a very natural manner. Basically, you just send Z to Z. Or if you like, they're equivalence classes. So you can either think of twistor space as that slightly complicated open neighborhood inside CP3, or you could just think of CP3 as this more global object, and that's perfectly fine. I think most people in the Amplitudes community prefer to think of twistor space as the whole of CP3. You can, if the definitions confuse you, you can of course ask me in the discussion session. We can do some examples stuff. So basically what happens is this embedding manifests twistor space as CP3, and in fact it's an open neighborhood of CP3 which you get by excising the CP1 of points where lambda alpha is 0. Basically this set is a CP1 because it's coordinatized by all those z's where you have the mu alpha dots, but you have set the CP1 to 0. And up to scaling, these are just C2s up to an overall scaling, so these just form a CP1. And if you excise this CP1 from this CP3, you get exactly the embedding of twistor space PT into CP3. This P secretly stands for projective. And this is why I went through all this, just to give you the name of the space. Any questions about this? This is just fun geometry. You can forget about it if that confuses you. But I'm happy to answer questions. Okay, so the meat of the subject, the reason why I had to talk about CP1s in CP3s is the so-called incidence relations. So now we come to the meat of the subject. Incidence relations. Maybe they now have to end. Oh, okay, we'll see. So, I started with complexified Minkowski space. So that was C13. And I have constructed twistor space I can construct the copy of C13. Now I'm going to draw what is called a double fibration. So construct the consider the Cartesian product C13 cross CP1, where this CP1 has coordinates lambda alpha or equivalence, scaling equivalence classes of lambda alpha. There's a projection, and this C13 has coordinates x alpha alpha dot. There's a natural projection map which takes x alpha alpha dot and forgets about lambda alpha. So this is just proj, which takes you to x alpha alpha dot. Think of this as coordinate on this Cartesian product. But there's another natural map which takes this data, x and lambda, and takes you to the associated twistor. This is the more formal way of setting up the correspondence rather than this angular momentum based way. So the map that takes you to the twistor is that you go to ZA equals, well, okay. You go to lambda alpha and you go to mu alpha dot equals x alpha alpha dot lambda alpha. And this, the scalings of lambda are now go to the scalings of this overall twistor, as we showed earlier, which allows us to think of this as a subset of CP3. This object, for a fixed x, this object defines an embedding of this CP1 into PT. And so, which board was I on? If you think of the sphere of lambda alphas as your celestial sphere, which you can do because the lambda alphas were a chiral half of your null momenta. So physically, you think of the CP1 of lambda alphas as the chiral half of your complexified celestial sphere. Then that map gives you an embedding of the celestial sphere into twistor space PT. How? You fix an x, take any fixed x in C13, then you basically get a map from CP1 coordinatized by lambda alpha into PT, which is given by mu alpha dot equals x alpha alpha dot lambda alpha. And this embedding of the celestial sphere of x, okay, so you can identify this CP1 as the chiral celestial sphere of the point x in complexified Minkowski space. And this embeds this celestial sphere into PT. And okay, you can people use various notations for this embedding. Some people like to use CP1x to signify that this is the celestial sphere of x. Some people just like to say Lx, which is what I'm going to do. So I'm just going to call this embedded CP1 as, okay, this thing as Lx, by which I mean a line. So this looks like a linear equation that determines mu in terms of the lambdas. So people like to call it a projective line. Secretly, it's just a two-sphere. But it's called in mathematical parlance a twistor line. So what it does is takes your PT and it embeds CP1x or Lx, the celestial sphere of CP1, into that. So now, the hope of celestial holography would be to construct some sort of theory whose fields are naturally living on CP1 but are functions on PT. Well, okay, I'll come back to that in lecture 5. Any questions about this embedding? This is called incidence relations. This is the most important take-home message of the whole lecture. What we're going to do later on is sort of start integrating over the celestial sphere and then start building various fields on space-time by giving data on PT, integrating over the celestial sphere, and getting a data at a particular x, so to speak, the x that's associated with that sphere. Any questions about this definition or projective spaces? Just the basic geometry. Sorry if it was a bit fast. This is just kinematics at some level. We'll come to dynamics in the next lecture.
So this embedding, you just keep lambda as it is.
Yeah, exactly. So lambda stays as it is.
And
That's why this is still coordinatized. We still use coordinates lambda alpha on this. And mu basically runs for a fixed x. Mu runs over all lambdas, and that gives you the points on the night sky embedded into this bigger 6-dimensional space. Did I tell you that that's 6-dimensional? So basically, that object is C2 cross C2, so that's 4 complex dimensional, so 8 real dimensional quotient by C star. That brings it down the real dimensions by 2. This is a 6-dimensional, 6 real dimensional space. Any other questions? I wanted to talk about reality conditions, but they're not that important, so I'll just send it to you in the notes.
So actually, out of curiosity, I think I've read somewhere that the Barket-Taylor formula is somehow complex alignment Twistor space.
Complex?
Like, I think is the simplest object in Twistor space, which is like a line.
On a line, yeah, exactly.
In which sense, like, I mean, I guess it's related to this too.
Yeah, exactly. So what happens is it gets localized on these celestial spheres. So there's this thing that in celestial holography parlance, some of us say that the points get pinned to the celestial sphere. So if you have n momenta, lambda alphas, and in Minkowski space, they're complex conjugates, lambda alpha dots, they all sort of, in the MHV, in the Park-Taylor configuration, they all sort of localize on a single celestial sphere associated to some x, and then you integrate over all x's to get a sort of.
What is local? Because I have in mind the Barket-Taylor formula, which is just, like some square and spinor brackets.
Yeah, I will probably mention that in lecture 4, so I don't want to jump the gun. But that's the idea is that you define some sort of real slice of twistor space. This is in the paper by Witten, by the way, which you might remember from 2003. You take the Park-Taylor formula, so that's some amplitude times a delta function of momentum. Then you write this delta function as integral d4x e to the I p dot x. And so you think of this x as some sort of coordinates on space-time. You take this an inside. And now you do something called a half Fourier transform, which I didn't want to talk about. So x alpha alpha dot lambda tilde alpha dot. Since I'm working in the complexified case, lambda and lambda tilde are complex variables, but there's a real version of this whole thing, in which case lambda and lambda tilde are real 2-component objects which you can Fourier transform in. And if you Fourier transform in the lambda tilde, the natural Fourier dual is that mu variable. And then when you Fourier transform, you get some delta functions that make the final answer look something like integral over d4x, product over I running from 1 to n, the number of particles, delta 2 of mu I minus x alpha alpha dot lambda I alpha. So you get the incidence relations back in this case, but through some Fourier transform in the lambda tilde. This is dual Fourier conjugate of lambda tilde. It's a bit complicated, so I'm not going to mention it. I'm not going to need it for celestial holography purposes, but this is where the motivation for Witten's twistor string theory originally came from. So in some sense, is the sphere a worldsheet? Are we're thinking of spheres embedding into some other space that sounds a lot like having a worldsheet mapped into some target space. So it starts sounding like a string theory. And this is exactly what I'm going to do in the last lecture if I have time. I'm going to do a more modern version of the string theory where instead of Witten's twistor string, I'm going to embed my sphere into ambi twistor space, which is the space of z and w's combined.
So does that mean that the imaginary part of the lambda
It's not defined in the complex case. We usually just take lambda and lambda tilde. This is usually done not in Minkowski space, but in 2-2 signature spacetime, where lambda and lambda tilde aren't complex conjugates of each other, but instead like two-component real independent objects. So you can actually independently Fourier transform in just the lambda tildes, real Fourier, just normal Fourier transform. That all that makes sense. I don't think anyone has sort of managed or even cared to sort of generalize it to the more complex case. But the more complex case has better behavior. If you work into 2 signature, you get science and random stuff. Things get ugly. But yeah. Okay. Any other questions? Still have 2 minutes.
So for each x, we embed the CP1 into the projected space.
Exactly.
If I change x, can I think of it as just placing this here somewhere else in the projected space?
Exactly. You sort of vary x. Yeah.
But that is what I would do in C13 cross CP1, right? That's the intuition I have.
Yeah.
But here it's different because this is 2 dimensions lower, this projected space.
Yeah.
So in a sense,
This is the only data you actually need, the sort of on-shell.
So as I vary x, is it the case that some of these spheres are identified?
Yes, exactly. And so it turns out that the only data you need is this. Yeah, for multiple x's, you get the same sort of chiral half of the celestial sphere. So the point is that the full celestial sphere is now complexified. So instead of CP1, it's just CP1 cross CP1. So the full celestial sphere will be different because that will have coordinates both mu and mu tilde. Or, okay, lambda and lambda tilde. So the full celestial sphere isn't the same, but the chiral half gets identified. The lambda tilde half is not visible in twistor space, it's sort of visible in dual twistor space, which you would define analogously. And that sort of, I don't know, circles around like a planet around the sphere. That's just intuition anyway.
Like how I'm not dealing with the lambdas.
Exactly. And it'll turn out that this is enough for our purposes quite beautifully until the last lecture. I'll do a couple of exercises in the discussion session if anyone is interested, but we can also just do questions. If people haven't seen project spaces before, it's useful to ask questions and stuff. I can do some examples, basic coordinates. Okay, thanks. I'm taking a break.